The last thing we will discuss is related to the nightmare of IPv6 versus IPv4. This module is called tunnels, because if time permits, we will look at other tunnels. So tunnels are, by definition, synonyms to encapsulation. So whenever you put an IP packet in UDP, or an IP packet in TCP, or an IP packet in IPv4 and IPv6, or IPv6 and IPv4, whenever you do that, we say that you have a tunnel. So tunnel encapsulations are similar. And typically, when you do that, that means you're violating the natural order of layers. Normally, TCP is on top of IP, not the other way around. So if you do it the other way around, we see that we have a tunnel. In theory, we never do that if we have a clean architecture, but in practice, there are always things in the corner that might force you to do. Those things in the corner might be security. So security might be why we have VPNs. If I access my company network from the outside, and I'm using my company computer, for example, some companies, they prevent your computer from working on anything else than the intranet of the company. So if you use it at home, you first need to connect to a VPN server of the company that will put all your traffic inside encrypted payload, perhaps if they use OpenVPN inside TLS, that will use a security layer on top of TCP, and then your IP packets that will be further put into the enterprise network. So that's for security. Another reason might be for private networks. If you have private addresses, and you might very often combine the two. And what we'll see now is private networking. So let's skip this one. Not private networking, V4 and V6 interworking. Today we'll talk about what is called like-to-like access. In the previous weeks, we've studied interworking. We've seen two methods of interworking, which are application layer, through application layer gateways, and through NATs. What we see today is a different thing. So the different thing is like-to-like. So for example, 6 to 6. So assume you have IPv6 at home, and you need to go to IPv6, to an IPv6 system, but your home network is IPv6, but the rest of the internet service provider gives you IPv4 only, for example. This is what we did for you in INF 019 when we have put in place an IPv6 island that is connected only to the IPv4 internet. And then we want to connect to the rest of the IPv6 internet. So in this type of problems, usually we consider that there is one thing called the IPv6 internet. There's only one IPv6 internet. And then there are islands. Anything else is called an island, and it's typically a small thing like you at home on your infrastructure. Similarly, there is an IPv4 internet. When we say the IPv4 internet, it means all IPv4 systems here are interconnected to each other. So that's a frequent problem today. We have that in INF 019. Some providers, like Free in France, have a similar problem when they want to give IPv6 connectivity. So they say, we give IPv6 service to everyone, but their backbone, in fact, is IPv4 only, because changing the backbone costs a lot of money. Cisco charges huge amounts of money for any change you do to anything. So they really cheat. They give you a box at home that provides IPv6, but their backbone is IPv4 only. So how do they manage that? Well, they have to solve the problem that we call like-to-like access, because we're not trying to convert your IPv6 packets to IPv4 packets. We're just carrying them over an IPv4 infrastructure. In the future, you might have the converse problem. If you're in a part of the world where you have only IPv6 access, and you have somewhere a machine that works only with IPv4, for example, the same ISP might have a similar problem for legacy customers and old equipment. The method is to use tunnels, so that's the trivial part of the method. So if I have a router here, then I will assume that this router can connect to my IPv6 island and to the IPv4 internet. Therefore, it's a dual stack router. It can do both, but on one interface here, it does only IPv6. On that interface, it does only IPv4. And what we can do is configure a tunnel between this router and that. So that router, IP46 router, is a gateway between the IPv4 internet and IPv6 internet. This one is a private router. This is a standard gateway. It has an IPv4 address. So what I can do is configure a virtual interface in this router, which will be an IPv6 virtual interface over an IPv4 physical interface. And practically, that means that if I do Wireshark here, here, or there, I will see when I send a packet, or when this is Homer, sends a packet to Lisa, the destination address will be Lisa's IPv6 address with whatever is contained here. And this will be carried inside an IPv4 packet, where the destination address of this IPv4 packet is router B. This is violating all the principles we've seen. The IP destination address in an IP packet is normally not the IP address of a router. But in this case, it is, because we have a tunnel. And then the protocol will be 4.1, which means IPv6. So that means inside the IP packet, there is an IP packet. That would be the simplest way to do it. Now, if we do this, what do we need to do? Well, we need to solve three main problems. I mean, first, we need, as we've said here, to have those relay routers. Now, A is easy. That's at my equipment at home. I need to have a router that's able to solve the problem. B is a bit more complicated. B is in the middle of the internet, or at the boundary between IPv4 and IPv6. So it's a bit more complicated. We'll see that this one needs to be special. Both are called relay routers. So a relay box is often taken as a synonym to router. Here the terminology is important. What we call a relay router is a router that is terminating a tunnel and decapsulates or encapsulates. The second thing we need to do is IP address allocation, because my provider is giving me only an IPv4 service. How do I get an IPv6 address here? And if you've looked at the IPv6 address we had in INF 019, they are special IPv6 addresses. They are not IPv6 addresses of the IPv6 block of addresses that is allocated to EPFL. They belong to a different block. That's the second problem to solve. And the third problem is we need to manage those tunnels. And we'll see that here it's possible to do what is called automatic tunnels. In other ways, A does not need to keep any state information about where to send the packet. In particular, in the previous slide, I showed that the IP address of B was 1234. So how does A know that it needs to send those packets to an end of tunnel that is called 1234? So this is what is solved by having the tunnels automatic. There are two solutions to this problem. The current solution is 6RD. But what we will explain is 624, because 6RD is the same, but with a few complications. So 624 is, I would say, the standard solution of 10 years ago that is deployed, for example, in the network of switch. But providers today prefer 6RD, and I will explain what's the difference in a minute. There are other solutions, Teredo, Isatap, etc., but we will talk only on 624 today. Just be careful. 624 might be misleading. We're not. When I hear 624, I think I convert 6 to 4 or 4 to 6. Right? This is not what we're doing. Right? It's 6 over 4. So a better name would have been 6 over 4 or 6 to 6 over 4. So 624 solves the allocation problem by using a special block of addresses that starts with 2002. I said 10 years ago. In fact, it is 14 years ago. 624 was standardized, and therefore they call it 2002. Although now that you're familiar with hexadecimal numbers, you know this is not 2002 because this is hexadecimal, but this is how things are done. So this block, 2002, followed by 32 bits, so a prefix of 48 bits, is the prefix that we use when we use 624. So 2002 means anything that starts with this is a 624 address. And the following 32 bits, as you can imagine, are simply derived from an IPv4 address. For example, if we have this EPFL address, when we translate it into hexadecimal, we obtain this. So this is a 624 prefix. So and the bits, this I said already. In addition, so in some sense, 2002/16, that means those 4 hexadecimal digits, are a block of addresses that means IPv6 means 624 host. There is another special address, or special block, in fact, 192.88.91/24, but only the .1 is used, which is reserved for the operation of 624, and it means the IPv6 internet seen from the IPv4 internet. So we'll explain that here. I'm taking the same picture as before. Here I have my local IPv6 network in INF 019, for example, the IPv4 internet, the IPv6 internet. The relay router that this provider, for example, Switch, which is our provider, has put in place relay routers that are connected to the IPv6 internet. So they have their own IPv6 address that belong to the block of Switch IPv6 addresses. It has also an IPv4 address, which is in the block of Switch IPv4 addresses. Plus, it has a second IPv4 address on the same interface here, which is this one. It's an anycast address. Anycast means the same address can be used by different interfaces. All such routers, obviously there must be more than one, just for reliability. Switch has certainly at least 2, and there might be other companies that have similar routers, so there might be a large number of routers that have this address. So if you do a trace route to this address, for example, you will not necessarily find this one. You will find the nearest IPv4, v6 relay router nearest to you. But having a fixed address for that simplifies, makes the tunnel automatic here, as we will say here. So let's look at this guy here that is on its IPv6 island. Well, the first thing is that because the router receives IPv4 service, it has an IPv4 address, 1234. At TPFL, it will be a bit different, but I take 1234 to simplify the mapping. Then we take this IP address and we construct an IPv6 prefix, 2002, 0102, 03, 04. That's my prefix, and that's the prefix I can use for me in this private domain. That's what we did in INF 019. We took the IPv4 address of the router that interconnects this room to the rest of EPFL. We constructed this prefix, and bingo, we have an IPv6 prefix for us. We can do that kind of things with IPv6 because the address space is huge, so we don't hurt really the IPv6 address space by taking away that fraction here. So all machines here now will belong to that prefix. So this router is an IPv6 router on its left side. So it will do all the standard thing that we've seen for IP address allocation with IPv6. So in particular, if it does automatic address allocation, when this host will boot, it will talk to the router to find this prefix, and it will have an IPv6 address, which will be this one, plus whatever other rules are decided by the local management inside this domain, and the host part of this address. So note that this machine has an IPv6 address that contains an IPv4 address, but its IPv4 address is not the IPv4 address of this machine, but is the IPv4 address inherited by this machine from its local access to the IPv4 internet. So that solves the problem of IPv6 address allocation. Now, Bart here is also alone on the internet, but is not going via a router, but is natively connected to the IPv4 internet, and like we can do when we are on the EPFL wireless network, and wants to run IPv6. Then you can do the same. You can enable a 624 interface on your machine, and you will inherit a 624 address that is derived from your local IPv6 address. So you can run IPv6 when you are on IPv4 with this system. Again, here you will not solve the problem of interworking, but since you are on IPv4, you speak IPv4, and if you run IPv6, that means you can also speak IPv6, but your only problem is you don't have IPv6 connectivity, which is today's problem for most modern. If you have a very old system, you might have a system that does not have IPv4, but all systems that are less than 10 years old have IPv6, so that's the standard case that allows you to communicate and have IPv6 to work. So how will thing work? As I mentioned, this router has this well-known IPv4 address. I said this address is in fact, in the IPv4 world, it signals, this behind me is IPv6. Because it means if I send a packet to this address, I will reach a router that's connected to IPv6 internet. So it means IPv6 in the world of IPv4 addresses. Similarly, the router B will announce, in the sense of the routing protocols, if it runs OSPF or RIP, it will announce the prefix 2002 into the IPv6 internet, which means that if this guy, if Lisa is sending a packet to H1 or to H2, the prefix starts with 2002, therefore, shortest path or whatever routing in the IPv6 internet will reach B or another router like B, that is a 624 relay router. A 624 relay router means a router exactly like this one that does this address on the left, injects 2002 on the right, and is able to encapsulate and decapsulate. Which means that if I send a packet now from 5 to H1, for example, the destination address is this one. So we can send to this guy as if everything was pure IPv6. Now, by the virtue of routing, it will reach one of these routers that now will know, because it's a relay router, it knows I have to send it to over IPv4. Conversely, let's look how things go from H1 to H3. So if H1 has a packet to send to H3, to this address, then Homer's PC, which is configured with the local subnet mask and everything, like in the Internet Engineering Workshop, will see, oh, this is not on link with me, therefore I need to send to my default router. So it will send to the default router. And then, where is A? A, so here, which is this address here. Now A, this router now is an IPv6 router from the left. It has received an IPv6 packet and needs to forward it. Now there is a problem that is solved by the tunnel, and we will see now how the tunnel can be created automatically. In its configuration, because it's a 624 router, it has a default route, which is this one. Now what is this? Well, if you are careful or very smart, you can immediately translate that, see that this is the hexa of the decimal notation here, which means I am a 624 router, not connected to anything else than IPv4. What should I do for IPv6 packet? I should send them to the IPv6. What is IPv6? Well, it's 2002. And then I need to put this because I need to create a tunnel. So that will be the default route will be to this next hop equal to this. So when this router has a packet to send to this destination is not in its routing table, means it's not in one of the configuration we've done, for example, in Internet Engineering Workshop. So it goes to the default. Default means next hop is this one. So I have to send it to this. Now, how do I send it to this? Well, it is a 2002 address that is not in my local domain. So I have to send it to this via a tunnel. And the tunnel is simple because I have already, in this route, I have the information of the IPv4 address. So we'll create an IPv4 packet with destination address, this one, which is the translation of this, As we know, the code doesn't use decimal, in fact, so there's no translation in the code. All the IP addresses, 6 or 4, are inside the code that we write in Python or in C, is already hexadecimal. So we'll create an IPv4 packet with this address, with the source, myself, of course, and it will go to the nearest relay router over the IPv4 internet. The router receives this packet. Now, because it's encapsulated, it has a destination address, which is this one. Then it's business as usual. It is on the IPv6 internet. It will reach H3. So we have done an automatic tunneling through the IPv4 internet. In fact, this router doesn't know at all who that router is. It just sends to that IPv4 address here, which is the IPv6 source address if we do Wireshark or TCP dump at 3 here. Close in 5 seconds. And the correct answer is C. Oops. Because IPv source address means the encapsulated address is, encapsulation means we take the packet and we put it inside here, an IPv4 packet, as if it would be a link layer, a layer 2 technology, for example. So of course, we keep the principles of IPv6, and this is the source that we should see here. So this, the IP address of H1. In the reverse direction, how does routing take place? I close in 5 seconds. Interference of applications. And the correct answer is B, of course. Routing takes care of it. B injects the 2002 prefix, and therefore all routers will simply find a route. So let me skip a number of things. So you can put yourself in the position of Bart, and this is what you would get on Windows, for example. You will get the 624 IPv6 address wherever you are connected. You can ping the nearest 624 relay router by doing ping to this address or a trace route here. We see that it's very close, so it means it's on EPFL campus, the net 624 relay router put by switch. From my home, that's another story. It's probably in Germany. And I will conclude with just this slide, and last slide of the year. If I ping from home the nearest so if we're at EPFL, we see everything as expected. The 624 relay router is provided by switch, who is our ISP. If I'm at home, my ISP, or the one I had at that time, that was Sunrise, doesn't have a 624 relay router because they don't care about that kind of thing, just do marketing. So the 624 relay router that's found is the one of some other provider, in fact, a German provider. So, of course, if you're a provider, you don't like that. I mean, if you are an advanced provider that provides 624 service, you don't want to provide your 624 relay routers for the other competing providers that are too lazy or too cheap to provide such a service. And that's the difference between 6RD and 624. 6RD is, in fact, exactly the same, except all the blocks and all the addresses I've said are not predefined and well-defined addresses. For example, this one is not a predefined address, but is an address that belongs to the domain of the ISP. So if you are Swisscom and you provide 6RD, then you will not use a default address like this one, but an address that is known only to Swisscom and to Swisscom boxes. Voila, thank you very much for your patience, and see you again tomorrow for 15 minutes of quiz. We had planned to do research exercise presentations, but bad luck this year. All the presenters are sick. Too much work, perhaps also, too much projects and congestion. So we will not do a research exercise presentation tomorrow, so we will skip the lab after the test. You will be free. Thank you very much. See you tomorrow.